Okay, 5.2. Do you see what I see? So we are going to look at how in the previous task, we first saw that we could create the following diagram by constructing and rotating triangles about the midpoint of its sides, with the final diagram suggesting that the sum of all of those three angles of a triangle adds up to 180 degrees, as you can see down around the point C, that vertex. This diagram tells a story because you saw how it was constructed through a sequence of steps. We even did carry it out ourselves, but sometimes we're asked to draw conclusions from a diagram when we're given the last diagram in a sequence of steps. We may have to mentally reconstruct the steps that got us to that last diagram so we can believe the claim the diagram wants us to see. So, for example, this first one, what can you say about the triangle in this diagram? Let's go ahead and maybe list a couple of things. Take a minute to list a few things. Think about parts of circles, what parts of circles that might exist in this diagram, this triangle ABC. Note that we have two circles that are circumscribed about the points A and B. And then we can come back together after a couple of seconds and look to see if you can figure out some things about the triangle. Well, hopefully the first thing that you see is that we have a whole bunch of radii of circles. So circle A has radii AB, or radius AB and radius AC. Circle B has radius AB and CB. Right? So we can see that those are all radii. Now, if we have those radii of a circle, we know that all radii of a circle are actually congruent to one another, right? It's part of the definition of a circle that a circle is the construct of points that are all equidistant from one other point. So it's every point that's equidistant from point A for circle A, for example. And that distance is the radius itself. So the radius, no matter where you draw it in a circle, the radius of that circle will be the same no matter where it's drawn. So AB, segment AB, is congruent to segment AC because of that. Now, also, segment AB is a radius of circle B. So if it's a radius of circle B, that means segment AB and segment BC are also congruent. So what does that tell us? Not only does this triangle look like it's an equilateral triangle, that actually can confirm for us that it is, in fact, an equilateral triangle, because if I were to color code this, AB is congruent to AC, and AB again is, let's do this, green. AB is congruent to CB. Now, if AC is congruent to AB and AB is congruent to CD, the transitive property of equality or of congruence the transitive property of congruence must state then that AC is also congruent to BC. So all of those three sides of that triangle are congruent, which makes it an equilateral triangle. So what convinces us that we can make that claim? What assumptions, if any, are you making about the other figures in the diagram? That kind of is what I just talked through right there, is that those radii are all congruent, meaning that the sides are all congruent. That also must mean the assumption kind of that I'm making, or the statement that I'm making, is that circle A and circle B are the exact same circle because they have the same radius. So what do we think is the sequence of steps that made this diagram? Now that's a question, right? What do you think the sequence of steps are that made this diagram? How did we get two circles around the segment AB with a circle at point A and a circle at point B, and then circle C where we have those two circles coincide up there at the top? So if we're thinking about this, here's an example of steps that we could kind of come up with. We could say, first of all, for number 3, let's say we had a line segment AB was drawn. So if I put that in notation here, geometric notation, line segment AB is drawn. So that's the first step. Second step could be that we've constructed a circle at center, with the center of A, whose radius is a length of AB. So circle A was constructed with a radius of AB. Okay, so we've got circle A now. In a similar fashion, we could also say circle B was constructed with a radius of AB. The last one here would be that point C up here, where those two circles intersect, has lines drawn to both A and B. So we could say segments CA and CB are drawn from point of intersection. Which, if we write that in geometric notation, would be segments, oops, not AB, segments AC and BC, sheesh, are drawn to the circles point of intersection. So those are 4 statements of how we could have gotten to circle A and circle B, and this triangle that's drawn inside of them. So let's now look at another case. What could we say about the triangles, quadrilaterals, or diagonals of the quadrilateral that appear in the following diagram? List several conjectures that you believe are true. Now, conjecture is just basically a statement that you think might be fact, okay? Also, it's cool to note here, they gave us that circle A is congruent to circle B. Now, that line there, or this little symbol here, that means congruence, right? It's an equal sign with a little squiggly line above it, and that means that circle A is congruent to circle B. Now, when we talk about congruence and equality, they're very, very similar, but equality is of values, so you're comparing 2 values, like the number 7 is equal to the number 7, right? We could say X is equal to 9. But when we're comparing shapes, those things cannot be equal to one another. Instead, shapes are actually congruent with one another. So circle A is a shape that is congruent then to circle B rather than equal to circle B. We can say parts like things about those shapes are equal to each other. So we could say a degree measure of that circle is equal to each other, or the measure of the radius is equal to each other, but the actual radii themselves would be congruent, right? But the distances of those radii would be equal. That's something that we'll continue talking about throughout this module as well, as we talk more about geometry and different things. So go ahead and take a few minutes, try to list a few conjectures or statements that you believe to be true about the quadrilaterals, the diagonals, and the triangles that are in here. Notice also real fast before you do that, triangle ABC, that's kind of the same triangle we had before, right? And now we have also triangle ABD that's similar to that, but turned upside down. So go ahead and take a couple minutes and give that a go. All right, so one of the things that we should have here is the idea that the quadrilateral is a rhombus. Now, a rhombus is a quadrilateral that has 2 pairs of parallel sides that all the sides are congruent. So it's basically like a square that has been squished a little bit. Now, if you change your perspective just slightly, you might be able to see that rhombus a little bit more. It's kind of a diamond the way that you're looking at it onset, but if you tilt your head about 45 degrees, you can see kind of that traditional rhombus shape. So that can be one thing you write. The quadrilateral is a rhombus. So go ahead and put that down. Hopefully another one that you came up with is that the diagonals of that rhombus, that quadrilateral, it appears that they bisect each other, which means that segment AP is congruent to segment PB and segment CP is congruent to segment PD. So those things cut each other in half, right? Those diagonals cut each other in half. And it's not that they are congruent to one another, because it's pretty clear that that horizontal diagonal is much shorter than the vertical diagonal, but instead that they just cut each other in half. So that means that we have two sides that are congruent to one another. Another conjecture we could write is that the diagonals might be perpendicular. They look like they are perpendicular to me, right? So we've got that right angle right there. That's another one we could write. And a final conjecture that we could probably write is that this angle right here is the same as this angle. Now, when we have two angles that are the same, basically that entirety of angle D, or another way to say it would be angle ADB, is cut in half. We have half of it on the right side, half of it on the left side. That would mean that that angle is bisected. It's cut in half, right? So we could say that segment PD bisects angle ADB. Or another way to say that is that those diagonals, PD or CD and AB, those are bisecting the angles of the rhombus. Okay, so those are several conjectures for us. What we need to do now is select one of our conjectures and write a paragraph that would convince someone else that your conjecture is true. Think about the sequence of statements that you'd have to make. So when I was kind of talking about this equilateral triangle up here, I made a series of statements, and you might even go back and review that portion of the video that said those statements, but you're looking for a sequence of statements that will help build on one another to support your claim. So for example, I said, well, AB is a radius of circle A. It's also a radius of circle B, right? Those are two facts that I'm stating. But now I'm stating, well, if those are the same, and I know that every circle has the radius that, or every circle's radius is the same no matter where it is, then I could say, I could make the conjecture, those two circles are congruent, right? Those are the same circle, just moved a little bit, right? Then I can also say, okay, segment AC is a radius of circle A. Segment BC is a radius of circle B. So by that same logic, AC and AB are congruent because radii of a circle are the same. And then I can say segment AB is congruent to segment BC because radii of a circle are congruent. Then I can say all three of those sides are congruent because radii of a circle are congruent and the transitive property of equality or congruence, okay? So that would be kind of a statement to say, this is why I believe this to be an equilateral triangle. All right, so what you're going to do is in number 5, I want you to write that paragraph right in that space of one of those conjectures, either that I said or maybe that you said about some triangles. If you made some conjectures about triangles, pick one of them and write a paragraph that you might convince somebody or convince me that that is a true conjecture. Now, I'm going to let you do this on your own, and then when I come back to class, we're going to try to talk through these together. So go ahead and take a little bit of time and write one of those down. All right, number 6, you have a second claim that you need to write a paragraph about. Now, this claim, you can refer to your previous paragraph if you think it supports the new one. So if you have some ideas that build on each other, you can use 2 paragraphs, or the second paragraph can refer back to the first paragraph in number 5 to kind of aid your argument here to state that your claim is true. So go ahead and take some more time now to pick another one of those. And go ahead and write that down and then come back together. Again, we'll talk about this when we get back together all together in class. Okay, number 7. Here's one more diagram. It says, describe the sequence of steps that you think were used to construct this diagram, beginning with the figure on the left and ending with the figure on the right. So it's saying, how could we create these diagrams? What do you think we could do to create these diagrams? So the first step I see is, well, we would have to have the segment AB. Okay, we would have to have the segment AB. And I see that segment AB is, here's that word again, bisected by that vertical line, right? So when I see these vertical hashes right here, that means that, and I'm going to label, let's see, I'm going to just say that this point is point M. kind of stands for midpoint. So I am seeing that segment AM is congruent to segment BM because of those vertical hash marks. So the first thing I have to do, though, is I have to have that line AB. So step one, draw segment AB. Draw segment AB. And that horizontal line right there refers to that as segment, right? Then I would need to locate the midpoint of AB. So locate segment AB's midpoint. Now that one might take some practice, right? One thing I could do is if I had this physically drawn on paper, kind of like we did by finding the midpoints of those triangles, you could fold it in half until those 2 points, A and B, coincide. And then where I crease that paper, that would be the midpoint, right? So I could do that. That's one way I could find the midpoint. We'll learn some more methods to find midpoints as well. But that's one way we could do it right now. Then C, the third step, is construct a line perpendicular to AB through that midpoint, M, right? So we see this little perpendicular line. So construct, which we'll learn how to do these constructions a little bit later too. Construct a line, a perpendicular line through the midpoint of segment AB. So that perpendicular line is drawn through that midpoint. Now I need to find, okay, how do I go from that left figure to the figure on the right? And I see that there's a point C. There are no real markings of measurement. There are no markings of equality or congruence. So for D, really what I'm looking at is all I need to do is just pick any point C on the line drawn through the midpoint. So pick any point C. On that line. And I'll say vertical line just to distinguish a little bit. Then E, what I need to look at is, okay, I've got to finish this up by creating segments AC and BC. So all I'm going to do is just say E is connect C to A and C to B with line segments. So there are some steps that I could have taken to draw these figures, right? So that's kind of the next step. Now let's look at number 8 in just a moment after we read a little bit about Travis and Tahani, our old friends. They're doing their math homework together. One of the questions asked them to prove the following statement. Now that word prove is interesting. When we're proving our point, we are trying to convince somebody that our point is accurate or correct, right? So we are here now trying to figure out how to prove this statement with Travis and Tahani. It says, the points on the perpendicular bisector of a segment are equidistant from the endpoints of the segment. Travis and Tahani think the diagram above will be helpful to prove this statement, but they know they will need to say more than just describe how to create the diagram. So Travis starts by describing the things they know, and Tahani tries to keep a written record by jotting notes down on a piece of paper. So they're going to go through and they're going to kind of just make some of these similar statements that I made with you guys just now, and then look at how we could say, okay, that proves that, for example, point C is the same distance away from points A and B. So in the table below, there are Travis's statements that Tahani took notes about, okay? So we're going to now try to figure out a symbolic notation of what Tahani may have written, kind of a shorthand notation, to keep track of Travis's statements. In the example given, also note how Tahani is introducing symbols for the lines and points in the diagram so she can reference them again without having to use a lot of words. That's something that we're going to do now going forward as well, is we want to use symbolic notation so that we don't have to say so many words in writing, but instead we can refer to lots of different things using symbols, kind of already like I've been doing with segment AB, where I don't really, if I'm looking at A, I don't really need to say draw the word segment and then AB. I can just use that horizontal line above the letters A and B to dictate that that means segment AB. So that's kind of what we're going to look at here. So Travis's statement, let's work from Travis's statement and then look at Tahani's notes and help to fill in Tahani's notes with some symbolic notation. Travis's statement says, we need to start with a segment that and its perpendicular bisector already drawn. So Tahani says, draw segment AB, locate its midpoint M, and then draw a perpendicular line L through the midpoint. So we named this point M right here, but Tahani goes one step further and names the vertical line L as well. Notice that that's a lowercase cursive L. That's a typical way to denote the name of a line. Now, Travis' second statement, we need to show that any point on the perpendicular bisector is equidistant from the two endpoints. So I can pick an arbitrary point, which means kind of just a random point or a point that doesn't really matter. It's just any point. It doesn't have a fixed distance on the perpendicular bisector, and we'll call it C. So Tahani says pick any point C on line L. Now Travis says in the next step, we need to show that this point is the same distance from the two endpoints. So really what we're looking at is if we come back up here, we're trying to say point C is the same distance from points A and B. So we are actually trying to say this line right here, AC, is congruent, meaning the same distance as this line, line BC. Okay, so that's what we're going to try to prove. Now, if I put that in notation, I'm going to say segment AC is congruent to segment BC. That's what I'm trying to prove. Now, Travis says if we know the two triangles were congruent, we could say that the point on the perpendicular bisector is the same distance from each endpoint. So what do we know about the two triangles that would let us say that they are congruent? So we need to first figure out, okay, what do we need to do to prove? Or what do we need to first prove, rather, before we can say that segment AC is congruent to segment BC? What do we need to do before that? And when we talk about congruent triangles, that just means that the triangle on the left, which we could call triangle ACM, is congruent to the triangle on the right, triangle BCM. Notice the way that I said those as well. It was ACM and BCM. So that means corresponding parts, that first line AC and BC that I want to be congruent, are spoken in the same order, right? So I'm looking to see that triangle ACM is congruent to triangle BCM with order preserved, right? That order matters. So what I'm looking at is I need to first prove that triangle CM is congruent to triangle BCM. Okay, so that's what I need to prove first. Now, we know that both triangles contain a right angle. So I'm going to just state that in symbolic notation. It would look like this. Angle CMA, which I use my vertex as the center of those 3 points, right? That's how I would talk about a point. The center letter is the vertex. So angle CMA and angle CMB are right angles. And that is due to the fact that we know that this is a perpendicular bisector, so we have that little right angle marking. Okay? So those are right angles. Now, Travis says we also know that the perpendicular bisector cuts segment AB into 2 congruent segments. So that's those little horizontal or vertical hash marks right here. AM is congruent to BM. So I can say that statement itself. Segment AM is congruent to segment BM. It was bisected into 2 congruent segments. Then Travis says, obviously, the segment from C to the midpoint of the segment AB is a side of both triangles. So he's saying this side right here, basically what he's saying is this side is itself, right? And it's a part of 2 triangles. It's a part of triangle BMC and it's a part of triangle AMC. And if a line is itself, then of course it's going to be congruent to itself. So what we can say there is segment CM is congruent to segment CM. Okay? So that line is itself. And then he says, so the triangles are congruent by the side angle side SAS triangle congruence criteria. Now that's a new idea here, but this is a conjecture or a congruence kind of statement that we can look at and say, okay, if we have a side, an angle, and a side that are congruent in two triangles, we could state that those two triangles are congruent. So we want to, I really shouldn't mark that in red, we want to prove that AC and BC are congruent. But what we know is in red here. We know that this is a right angle and that both of them are right angles, right? We also know that AM is congruent to BM, and we know that CM is congruent to itself. So now I have a side, an angle, and a side congruent to a side, an angle, and a side, right? That's where that SAS triangle congruence theorem comes into play, okay? So I'm going to erase those just for clarity's sake so that we don't get too convoluted here. But now I can state that triangle ACM, just like we had above, is congruent to triangle BCM. So now I wanted to first prove this. Check it out. Down here, I just have, based off of this side, angle, side, triangle congruence criteria. Next, Travis says, since the triangles are congruent, segments AC and BC are congruent. And that's this idea that if you have two things that are congruent, all of the corresponding parts of those things are also going to be congruent. We'll talk more about that idea in a while too. Whoops. But now we can say, okay, those two points, or excuse me, those two line segments, line segment AC is congruent to line segment BC, okay? Which again, that's what I'm kind of wanting to prove. So we've gotten to that point. Now, Travis finally says, that proves that point C is equidistant from the two endpoints. Now, because we didn't use any numerical values, we didn't put any numbers on this, this is the arbitrary case where we could say, okay, we could pick any point C. It could be, C could be right here. C could be over here. C could be this midpoint. C could be all the way down here. Those points are going to be equidistant from points A and B because of what the work we've just done. So then Tehani's final note there is that any point C on line L, the perpendicular bisector of segment AB, is equidistant from the endpoints of A and B. So Tehani thinks that Travis is brilliant, but she would like the ideas to flow more smoothly from start to finish. So what we need to do is arrange Tehani's symbolic notes in a way that someone else could follow the argument and see the connections between ideas. So that is kind of something I want you to do with me, actually. I'll do this with you guys, especially since this is kind of our first taste at a proof. So we're going to go ahead and I'm going to go to a notes section real quick, and we're going to arrange all of these thoughts in a more linear manner so that we can make a statement and then make another statement based on that previous statement and give also reasons. All right. This is the first idea of what we call a two-column proof in integrated math 2. So go ahead and if you need to pause this, grab a sheet of paper, pull a sheet of paper out because there's not enough room on here, and then start it up again when you're ready to tackle the next two-column proof. All right, so hopefully you are ready. A two-column proof is just that. It is a proof with two columns. So we'll go ahead and start it right here. Now these two-column proofs always have a statement, which is a statement of truth, and then they have a reason. So we'll label this left side statements and this right side reason. Okay, so we cannot make a statement without having a reason for having made that statement. Now, it's also important for us to state what we're given and what we're trying to prove. So the thing that we're given is we have line L, which is the perpendicular bisector of segment AB. And this is through point M, right? Through point M. Oops, let's say M. All right, so that's through point N. M. And now what I also want to know is I want to have my goal in mind. This is what I'm trying to prove, that any point C on line L will have this statement be true. Okay, so any point C on line L, that's that arbitrary point, has the statement true. Segment AC is congruent to segment BC. That is basically saying it's equidistant from points A and B. It's equidistant from the endpoints of that line segment we drew first. So let's start with kind of that same idea that we started with in Tahani's and Travis's proof. The first thing that they started with really is this idea that angles CMA and CMB are right angles. So let's write that down as a statement. So angle CMA and angle CMB are right angles. Make sure you write angles there and not angels as well. That's an easy thing to make a mistake. Now, how can we say that? So that's our statement, but why can we say that? And this is the idea of the definition of what it means to be perpendicular. We know that line L is the perpendicular bisector. So what we can say is those are right angles because that's the definition of being perpendicular. Or more concisely, that's the definition of perpendicular. Okay, so that's our first statement. Now the next statement that we made is the idea that we have two segments, AM and BM, that are congruent. And we know that that is because a perpendicular bisector cuts AB into two congruent segments. So I'm going to go ahead and say segment AM is congruent to segment BM. And why can I say that? What's my reason? That is actually the definition of a bisector. So our reasons have been two definitions so far, which is kind of handy. Now what I can say is I can also say that segment CM is congruent to segment CM. Oops. Oh no. Let's try that. So segment CM is congruent to segment CM. Now, this is an interesting idea. It's the idea that, let's say you look in a mirror. What do you see? You see yourself, right? You would see yourself. Now, you are the same as yourself in that reflection, right? You and the image you see in the mirror are the same as yourself. So that's this idea of, it's called the reflective property of equality. When you look in a mirror, you see yourself, you're equal to yourself, right? So the way that we say that in math is that CM is equal to itself, or congruent to itself rather, based on the reflexive property of equality. Okay, now we have this idea, if we come back up here to our figure here, we've now stated that AM is congruent to BM, we've stated that we have two right angles, and we've stated that CM is congruent to itself, which means we have that side angle side conjecture. So we can go back down here and say triangle ACM is congruent to triangle BCM because of that side angle side conjecture. Now, triangle ACM is congruent to triangle BCM. And we can use, rather than writing out side angle side, we can use that kind of abbreviated version of SAS. Okay, now because of that, because we have those two triangles that are congruent, we know that corresponding parts of something that is the same as something else will also be the same. So AC, segments AC and BC are congruent, or segment AC is congruent to segment BC. That's those two green hash marks right there. Segment AC is congruent to segment BC. And the reason for that is saying the corresponding parts of congruent triangles are congruent. Now that is a mouthful. Corresponding parts of congruent triangles are congruent. Fear not. Just like side angle side has an abbreviation, corresponding parts of congruent triangles are congruent, also has an abbreviation. That is abbreviated as CPCTC. Okay? It's a bunch of C's separated by PT. All right? CPCTC. And that is kind of a handy way to do it. So that is what we have tried to prove, right? We are trying to prove that segment AC is congruent to segment BC. Boom, we just did that. When we finish a proof like this, we go ahead and give it a sense of finality with these 3 triangular dots. That is saying we have completed this, okay? So that proof is now complete. Let's go back and look at our lesson. We have one more thing to do. Oop, too far. Number 10, would your justification be true regardless of where point C is chosen to be on the perpendicular bisector, and why? Well, what we did up here is we specifically, or I specifically so far, I chose these values and did not give them any actual distances. I didn't give them any numbers, right? If we look at this back in kind of the raw form it was given to us, it's given to us just with statements of congruence, not statements of equality, okay? No numbers are equal to each other. So because of that, it doesn't matter, kind of like I was saying earlier, it doesn't matter if C is right here, or if C is right here, or C is right here, or C is up here. Those statements will work regardless of where C is because there are no number values on those statements. So it will always hold true that any point on the perpendicular bisector, wherever I put C, will always be equidistant from the endpoints of that segment that the line perpendicularly bisects. Okay, so that can be your answer to number 10. All right, good luck on your homework. I will be back to answer questions on Monday. Go ahead and work on your RSG.